is I can't share it like how I share on Zoom. That's the only downside to this Blackboard
Yeah.
collaborate. So if you want to follow along with what I'm doing, you're gonna have to like on your laptop open a different tab and open up the 2019 exam, three practice exam,
Oh
so you can just
yeah.
follow along with the questions. Because I'm gonna have to use the whiteboard to try and draw it out.
Okay. Can we skip a bunch of questions also?
Skip what?
Like a bunch of questions, if
Yeah,
that's
we
fine.
whichever ones you want to skip, we can skip because most of this is like easy
Hmm.
questions. So yeah, we could definitely do that. So like you could tell me where you would like to start from in the 2019 exam 3 version A, and then I'll go off from there.
Okay. Um, just to make sure, right? The acidity periodic trend, it's like it points from the top left for the least acid, and then the bottom right of the periodic table is the most acidic.
Yeah, so let's say this. Let me draw a little periodic table. Wait, let me record this so you guys can see ENO, the F, and then below that ClBr, iodine. So acidity increases this way on the periodic table. It increases from left to right, just like electronegativity.
Okay.
And it also increases going down the periodic table. So acidity increases from left to right and from top to bottom.
Okay. Yeah, yeah.
And basicity would just be the opposite. So from right to left on the top part is the basicity increase. And from bottom to top is also the where basicity increases.
Okay. Yeah, that makes sense.
Yeah, this is the trend.
Yeah.
That's what
Okay. So, could I ask, could we start at 7 and then we skip 8 and then go to 9?
Oh, sure, we could do that.
Yeah.
7, I can't really draw it, so we'll talk about it. So 7 is which of the following molecules would produce this IR spectrum? So we're looking at an IR spectrum chart. Now, when it comes to charts like these, we already told you guys like specific signals to look out for. Like around the 3000 region, if you see a broad tongue, this lets you know that there's an alcohol involved, so an OH bonding. Also around that region, if you see like a weird beard, like it looks something like you got like all this going on, this is for carboxylic acid. Now around the 1500 region, like 1500 and up, if you see a sharp sword peak like this represents a carbonyl group, so there's a C double bond O somewhere in the molecule.
Okay.
So when it comes to the IR spectrum chart, we the first thing we look for is to see if we see these signals, and if not, that just means that none of it is present in the molecule. So let's look at the IR spectrum chart we have here. Does it look like we have an OH involved?
OH? No.
No, we don't have a broad tongue peak like that. We have this weird little peak here. So that means you can cancel out A and B since there's no OH. Now, we do have a peak region at 3000, but does it look like the beard for the carboxylic acid?
No.
No, it definitely don't look like that. It's much bigger. So we know there's no carboxylic acid involved. And another thing to look out for is the sharp sword peak. So that's between, I believe, like 1500 to either 1600, I believe. So do we see a sharp sword peak?
Yeah, we do.
We do see a peak, but remember that's between 1000 and 1500. That's not where you would see the sword peak for carboxylic acid. For this peak, you will see it between let's say around where the 1400 is to
Yeah.
1600, but we don't see a sharp peak there. So like from 1400 centimeters -1 to 1600 centimeters -1. If you have this peak, there's a carboxylic acid. We do not have a peak between those regions though. So that means we have no carbonyl group there. So far we can cancel out A, B, and D since D has a carbonyl group. Now we're between C and E. The only difference between these is E has an alkene in it, right?
Yeah.
So there's a special way you can tell if you have an alkene or not. We know that the carbons attached to the alkene is sp2 hybridized, right?
Yeah.
So at the 3000 region, like that mark, it's kind of, if you look at like the the recitation packet when we was learning IR spectroscopy, they have like a splitting at 3000 here. Now, if you do have like a small peak that looks like this, that means you have on the right side, I believe that's the sp3 CH carbon, the sp3 carbons. So that's like the carbons in the carbon chain, the CH2s and all that. And on the, no, this is on the left. Now on the right side, if you have a peak that looks, it's somewhat in size like this, it's kind of small, that means you do have an sp2 hybridized carbons, which is known for the alkenes, double bonds, and all that.
Okay.
So if we look at the 3000 mark, at 3000 we do have this weird peak in the beginning, but this is not the shape of the peaks for these peaks here for your sp32.
Yeah.
So that means we have no alkene.
And it's
We only have the, right, we have no alkene whatsoever in this molecule. We only have, the carbons in the carbon chain. So it's mostly made up of CH2 and CH3s. So the answer choice that matches that would be C.
okay.
Any question?
What do you say the what's the thing at the bottom left? What do you say the range was for that? The O and the OH thing?
Which one? For the carbonyl group, the COH? C double bond O?
Yeah, yeah.
Oh yeah, so I said the region to look out for that would be from like 1400 centimeters to 1600 centimeters. For OH, that'll be like between,
That's like 3,300,
let's
right?
say 26, yeah, because you see the numbers is going up from right to left. So let's say from 2600 to, let's say 3100, you will look for this OH peak.
Yeah, what about I forgot what the functional group was for the thing at the bottom left.
Oh, the carboxylic acid, I
Yeah.
believe it would be the same region. For this one, I believe it's like 2500 to 3000. It's around the same region as where the OH would be, but you can definitely tell the difference
Yeah.
between the two because the carboxylic acid, it looks more like almost like a Santa Claus beard, and OH is a broad tongue.
Okay. All right.
Okay, so for the SP3 and SP2, it had to be exactly at 3,000.
Yeah, so like if you look for the 3000 peak and you have to like kind of split it in half. Like use a dashed line and you look out for peaks that look like this. So on the right, not the right, I keep saying the right, on the left side, the peak is like, it characteristically looks like this. This lets you know that you
Charger
have
for what?
sp3 carbons. So like your
It's in my bag.
CH2s and all that.
It's in my bag.
And on the right side, if you do see a peak like this,
So
it
good
has
that
to
they're
look
still
something like
tied.
this. It can't look like what this weird blob looks like in the beginning. That lets you know you
Look at that
do
gully
have
though.
sp2 hybridized carbons, which would exist in alkene versions.
Okay.
Yeah,
Do
that
it.
makes sense.
Yeah.
Okay.
IR isn't too bad, but specifically, you just specifically look for these certain, signals that we know we can definitely tell what's what on the molecule,
What?
and that's about it. If you don't see that, the answer is most likely the molecule
Check
without
on the
what's
table.
missing.
Check the kitchen chair.
Yeah.
Okay.
Let's move on to.
Can we
You want to
do
do 8?
9 and then we go to 12?
Oh, sure.
Yeah, hopefully that's fine.
So, which of the following molecule is least acidic? So, let me draw on the molecules.
I have exam on Thursday. Damn.
N2H. So this is A, this is B, this is C, and then D is
The big pocket.
D right there. All right. So
What? Okay. Oh, good.
we're saying which of the following molecules is least acidic.
Very
Now,
good. Very good.
we know how acidity increases across the periodic table. So, in other words, this question is asking for which of these molecules is more basic. Right? Which one is more basic? Let me just draw in some lone pairs so we don't get confused. So, acidity increases from left to right on the periodic table. So, basicity is the opposite. So, which one of these
Shit.
answer choices do we know we can eliminate?
A
Mm-hmm.
and D.
And which one?
D.
Yeah, D. D you can eliminate.
So what was the question asking again?
So the question is asking which one of the molecules is least acidic. Now,
C.
the most basic molecules will have the more reactive electron lone pairs. And we know we have lone pairs on oxygen and nitrogens. So the more since acidity is related to electronegativity, that means the more electronegative atom would be more acidic, right?
So it will be C.
Right. We can cancel out B, and the
Yep.
answer would be C. The lone pairs on this nitrogen and C is definitely more reactive than the ones on D because of how far apart the carbonyl group is. Not the carbonyl group, the double bond. So because the C cannot resonate, these lone pairs are definitely more reactive than in D. D, it can resonate. It can create a double bond there, and this double bond can move down here. And anytime you can resonate, remember the electron energy is always lowered. But in C, it can't resonate, so the electron energy of these lone pairs are very high, which very reactive.
So if they would have asked me for the more acidity, it will be A
Wait, so if they ask for what?
for the more acidity.
Yeah, it would definitely be A.
Yo.
So it's like
What?
a pattern when you think of when you take
Hold
of
on.
acid and base. Bases, you're worried more about the electron
no.
pairs. For acids, they always donate protons.
What?
So
Okay.
it makes sense that A and B would be least acidic because we see their protons. Not would be acidic, I mean, because there are protons attached to it. Versus the C and D, they don't have no protons, so they would work more as the base than the acid. Well, they H2. But because of those lone pairs and the fact that N is less electronegative, they're always going to be very reactive on nitrogen. So it'll work more as a base than it would as an acid.
Okay.
Okay. Wait. So could I ask, right? If I originally saw this question, because I feel like compared to Hendrickson, I have a different point of view on this. It says least acidic. I would
Mm-hmm.
just cross out the oxygens, right? So I have C and D, and
Mm-hmm.
according to what you said, this is what I'm gonna remember in my mind for the exam. If it can't resonate, then it's least it has like less acidity. That's what you're saying with the double bond.
Right. That's right.
Okay. Yeah, I needed like the
If it
recap that.
can't resonate, it'll definitely be less acidic too, which will make it more basic
So it'd
because the
be
bases works with the electron lone pairs.
okay, and like you said earlier, it would be A if it's the most acidic because it's more.
Mm-hmm.
It could resonate. Okay, and it's oxygen. All right, that
Right.
makes sense. Okay.
All right. So you said you wanted to do 12, right?
Yeah, this is like on the second exam.
Yeah, I remember this was a good question. So, which is the highest energy conformation of the following molecule? So let me just draw in the. Oh, you had this cyclohexane. You had an ether, ethyl. I mean, not an ether. ET. You have a methyl on a dash, and right next to it, an ethyl on a OH. So we're
Okay.
looking for the highest energy. Oh,
So that would be the least stable,
right,
meaning
exactly.
more
We're looking for the least stable chair conformation.
Yo,
meaning more axial position.
Yeah.
fuck.
So when we're looking for the least stable chair conformation, instead of pushing the big group into an equatorial position, we're going to push it to an axial position. That's definitely going to give us the least stable. Now with this question, first before you choose which, because we see we have big groups that are the same. There's two ethyls. Ethyls is bigger than methyl. Now it's about which one of these ethyls we're going to push into that axial position. You want to push this one into the axial position. This will be carbon number 1, then 2, then 3, then 4, then 5, then 6. So you want to push the ethyl that's on carbon number 1 into the axial position. If you do the other ethyl, you'll see that you get a different chair conformation, and that's not going to be correct. So when it comes to figuring out the chair conformations and you have big groups that are exactly the same, you want to number the carbon first before you push it into a position because you don't want to get the wrong chair conformation. If, say, one of these ethyls was like a tert-butyl, you don't have to worry about numbering and stuff because we all know that the tert-butyl group is bigger. But in this case, number your carbons first and then choose the group closest or that's on carbon number 1 to push that into either the equatorial or the axial position. So that means this one is going to be axial.
Wait, why you? Quick
And
question. Why are you making it
mhm.
axial instead of equatorial?
Oh, because we're looking for the highest energy chair conformation. And in order for molecules to be in high energy, that means they're always going to be unstable, so least stable. So now we all know that in order for a chair conformation to be stable, we always try and push the big group in an equatorial side. But this time we're looking for an unstable conformation, so we have to force it to an axial instead of the way around.
Okay.
So this first ethyl is going to be axial, and since it's
Why
on a
would I
wedge,
ask
that
that?
means it's going to be axial up because it's coming towards us. So in order for it to be axial up, what type of carbon would this ethyl have to be on?
And the up carbon.
Right. The carbon has to go the same way that the substituent is going in order to be in an axial position. Opposites will always get you the equatorial. So since this one's going up, that means the other one's going down. Then this one's going up, then down, then up, then down. Any questions of what I did so far?
Yes. We always start with the if they give you two ethyl, right? We always start with
Mm-hmm.
that have like another substitute nearby, right?
Yeah, we always start from where the other substituent is. Like how this one on carbon number 1 is next to this methyl here.
Mhm.
That means we'll start with this ethyl first, because this would be the correct way to number the carbons. This would be carbon number 1, then 2, then 3, then 4, then 5, then 6.
Okay.
So now this methyl, it's going down because it's on a wedge, so it's going away from us. And it's on a down carbon. So what position is it going to fall on?
Axial.
Right. It's also going to be axial. And lastly, we have this ethyl here. It's on a wedge, so that means it's going up because it's facing towards us. And it's on a down carbon. So where is it going to fall?
Equa.
Equatorial.
Right. Equatorial.
Cool.
So now we have figured out our highest energy chair conformation. So if you want, you can even go further and draw it in. And let me see if I can draw it in good. Yeah, that's good enough. So carbon number 1 is up, and the ethyl is going up, so it's going to be like, no. Hey. Yeah. Oh, sorry. So it's going up. The methyl on carbon 2 is going down, and it's down axial. And then 3, 4, carbon's going down, but the ethyl group's going up, so it's going to be equatorial, so it looks something like this. And this is what our highest energy chair conformation would look like. So which of these answer choices match that?
D.
Yeah, D. D will closely resemble. So that's how you do this question. Any other questions about this question?
No.
All right, cool. So what else would you like to go over?
Can you explain like quickly? Because we're already,
Mm-hmm.
it's already like halfway through the session. Could you explain 13 and then 14?
Oh yeah, cool. So 13, which of the following bases would be least reactive? So what that's saying is basis, it deals with the electron lone pair that we see there. So now we look at each of these molecules and we do see that we have double bonds in play. So what's one thing you're going to have to focus on to determine the reactivity of the lone pair?
The resonance?
Right. You're going to have to take resonance into account now since we do have those double bonds. So since we're looking for the least reactive lone pair, that means the lone pair that can resonate the most, that's going to be the least reactive. Because remember, the more a molecule can resonate, the more lower its electron energy is going to be, which is the least reactive that lone pair is going to be as well. So when you try this question, A, B, C, and D, just try and figure out the movement of the lone pairs and see which one could resonate more than the other. And the ones that can do that, that would be the least reactive.
They just like to do things backwards.
Hmm?
They just like to do backwards, like least reactive, more resonant. Wow.
Yeah. Yeah. Least reactive, more resonance.
Okay, yeah, that's a good trend.
Mm-hmm.
I'll probably, you're fine if we don't go over it, right, for time. I'll like find out how to do it.
Mm-hmm.
Yeah. Okay. Thank you. Can we try
You're
14?
welcome.
There
Yeah.
was,
So
yeah, when there was PKA stuff on the second exam, I had no clue what it what it meant, to be honest.
it said which carbonyl containing function group has the most positive pKa. So we have a ketone, an amide, an ether, a carboxylic acid, and an amine. Amide and amine. I think some of these listed here, because I remember from exam 2, he gave you guys like a chart for all the pKa's of whatchamacallit, hold on, let me see if I can find the chart. I think I'm looking at the paper right here. All right. So yeah, I would get to look at this chart a little. So you guys still have your versions of the exam 2 that you took, right? Like the physical paper?
I'm looking for it right now.
Yeah, because the chart in the back, it would help you. Like to try and figure this out, like mathematically and stuff, we didn't do any of that in class. So what I would do is, because I do see this question asked a lot, sometimes I would just try and study the chart for these specific functional groups and just remembering the pKa for them. So like for example, for a ketone, the pKa, let me write it down. Ketone, the pKa was 20 to 24, is 20 to 24. And what he said, an amide, what's for an amide? That's if it's listed here too. Some of these functional groups are not given to us, so amide group ether, is ether listed?
The amide pKa, I googled it. It's like around 20. It says.
Okay, so let's say 20. For ether, ether is not listed here neither.
That's weird.
Yeah, so it's like that though. Some of these functional groups, they don't really give you the pKa like that. The reason why too is because like if you look at amide and is ether like that? Or is that an ester? No, that's an ether. They're like carboxylic acid derivatives. That's what they're known for, because they have the same carbonyl group function as a carboxylic acid. So
Okay.
like this was an amide, and then the ether looks like this. Oh, let me just put R for R group. So I believe if that's the case for an ether,
It says.
that means it's around 20, right?
It says negative 3.5 for ether
For an
pKa.
ether?
A di. I don't even know what this says. It just says negative 3.5 pKa values for organic and inorganic Bronsted acids at 25 Celsius.
Okay. So in the mean we see here, that's 35. And then the last one we said was carboxylic acid. Is that one is listed? Yeah, that one's listed here. That one's 4. Funny. So ketone between 20 and 24. Amine we had said was around 20. Ether was negative 3.5. So ether we can automatically cancel out because we're looking for the most positive pKa, not the most negative. Amine is 35 and carboxylic acid is 4. So then the answer would be amine, which is the most positive.
Wait, but you say negative 20, 35.
Which,
Oh no.
no, that's not a negative. That's that little squiggle, it means about. Yeah.
Yeah.
When it's a straight dash, like if you look at sulfuric acid, for example, that's a -3. But when you see that little squiggle, this means about. So it's about 35 for an amide. So the answer for 14 is E. I almost said D.
Okay.
Yeah. So, are there any other questions you want to go?
Just to make sure, 15, right? Staggered.
Mm-hmm.
Sorry if you hear like screaming in the background.
That's all right.
What's it called? So staggered is the normal looking. For 15, staggered's like the normal looking figure, and the other one I forgot what it's called. Gauche, right? It's like the.
Yeah.
It's like
So
the.
staggered and staggered gauche, they all have the most spread out bonds. So let's draw an example of each. Let's say I have dang it, stop moving. Let's say I have a CH3 H or H there. HCH3. This is staggered. When you have two big groups facing away from each other, this is known as the staggered anti. Then you have the other staggered version. Say, let me draw it the same way. Now let's say we did a 120 rotation with the big carbon in the back. So the front I'm gonna keep the same. Then that means this hydrogen ends up here, the other one ends up here, and then the methyl ends up here. This is staggered gauche because the two big groups are next to each other. They're still pretty far apart, but they're still near. So it's staggered gauche. Then we have the eclipses. So let's do an example of the eclipse. That's when it's a little closer together. So let's say we're about to rotate it, right? I'm gonna draw this methyl a little closer here. You'll see it like slightly off to the left. This is eclipsed. This would be the high energy eclipsed because of how close together the two methyl groups are. And then you have the low energy one, which looks like this. So let's say you have CH3, then you have H, you have CH3 down here, and then the other H is right here, I think. So let me draw this one on the other side. There. This is your low energies because now the two methyl groups are away. But just remember that the eclipsed Newman projections are always higher in energy than the staggered.
Okay.
Within each of these Newman projections, you still do have relative energies, of course. The staggered anti will always be the lowest energy conformation.
All right. Yeah. So the answer for this would be D. Or 15 then, because the high energy eclipse, the one where they're close to each other, essentially it's like cis, is the highest in energy.
Yeah, so 2 should be, so you have these Newmans A, B, C, and D. A is eclipsed, you could tell. A and C are eclipsed, and B and D are staggered. So C would be placed where 2 is. So let me do it. They have the energy levels 1, 2, 3, and 4. So C, that's the high energy eclipse because all those methyl groups are right there next to each other. So C should fall on the 2. Then the other eclipse one we have is A. A is lower than C, so that should be 4. Then you have B and D, which are the staggareds. D, even though you have these 2 methyl groups here that are close to each other, you still have one methyl group that are farther apart than the one in B. In B, all the methyls are together. So that's the high energy staggered conformation. So B should fall in 1, and then D is 3. Yeah, cool.
Yeah, that makes sense.
Yeah. All right, cool.
I don't know how to do it.
Hmm?
Number 16. I don't know how.
16.
Yeah.
So it says, consider the following homolysis reaction. So that's when the pi bond breaks and both electrons are shared equally back to the 2 electrons to the 2 atoms that the electrons came from, instead of 2 going to 1. So consider the following homolysis reaction, which is least endothermic. Least endothermic. So for an endothermic reaction, let me just write down. For an endothermic reaction, energy is being absorbed, is not being released. So energy is absorbed. This is the least endothermic. So looking at each of these answer choices, one of the periodic trends you're definitely going to have to focus on is electronegativity, because we see we're working with fluorine, oxygen, nitrogen, and carbon. So hold on, give me one. One minute.
So D, because it would be the far more to the left.
Right. So for endothermic reaction, not a lot of energy is released. So the weakest bond breaking would be the least endothermic. Yeah, D is the answer though. This H3, this CH bond breaking, this is the least endothermic reaction.
Yeah, that makes sense.
Mm-hmm.
Can you tell me the trend for bone strength again? That's a
Oh yeah, so bond strength. Let's go over some trends. HCNOF.
increase with electronegativity, right?
Right.
The same way.
So electronegativity increases left to right on the periodic table. Bond strength also increases left to right on the periodic table. And acidity increases left to right on the periodic table. There's something else that increases left to right to the periodic table. I believe that's ionization energy.
Mm-hmm.
So ionization energy, that also increases left to right on the periodic table. Remember, that's the energy that's required to take electrons away from an atom, like high energy electrons away from an atom. Wait, does that? No, decreases left to right then. I believe it increases the opposite. No, I was right. Increases this way because as electronegativity increases, remember the electron energies is lower. So that means the reactivity of those lone pairs that you're going to try and take away, they're going to be lower in energy. So around the region going up, you won't really find much high energy electrons. So the ionization energy definitely increases left to right on the periodic table.
Yeah.
Yeah.
Okay. Okay. Could I ask? It's for a question in the exam. Could you
Hmm.
go over? Let's see. Could you do 22 and then 23?
Let me see.
Which are the following?
So 22. Which of the following statements about the equilibrium below is true? So you have this reaction. I hate when this happens. It's negatively charged. You have one there. Plus. So you have this reaction here. Looking at it, you can see that
Okay, I see.
your propene in the beginning, I believe this acted as your acid. And then this acetone here acted as your base because we
Whenever they
do the
give you a
wrong
big,
thing first. This is a negative because you end up with lone pairs here.
whenever they give you
Con-
pKa main acid, right?
Hmm?
Whenever they give you like say propane, pKa, it will be in that
Mhm.
acid.
Yeah. Yeah, so that was the acid. And the other one acted as the base because we ended up with a lone pair on one of the carbons in the propene. So this became a little anion, and then this is acetone. This is acetone enolate. So 1 says the equilibrium will lie on the left. 2 says the equilibrium will lie on the right. 3 says the allyl anion is the strongest base in the equilibrium. And 4 says propene is the weakest acid in equilibrium. So which of the following statements is true?
One is true. 3 is
I
also
lost the
3.
page.
Okay.
Yes, 1 is true. The equilibrium will lie on the left. It always lies where the
Weaker.
pKa is more, yeah, and where the pKa is more positive, that's always where the equilibrium lies. More
Okay. So
positive.
more pKa means it's weaker.
more positive.
So
pKa.
yeah, the more the pKa is, the weaker the acidity. So it always the equilibrium will always lie on the side where the acid is the weakest.
Okay.
So that'll be to the left of this reaction here. So 1 is true. That means we can cancel out 2. Now 3 says the allyl anion is the strongest base in the equilibrium. So that's this molecule here. Can we say that that's true?
Yes, because
Yeah, definitely.
strong acid react with strong base.
Right.
Wait, can you say that again?
Wait, not all the time. Sometimes you have weak acid-base reactions here as well. But when it comes to figuring out which ones is the strongest base, remember the electron lone pairs that fall on the least electronegative atom will always be the most basic because it's more reactive. So we do have a negatively charged electron pair on a carbon, which is definitely the least electronegative atom. So that's what makes it a very strong base. These lone pairs are very reactive on the carbon. So when you're trying to figure out which of the atoms is more basic, just think to yourself, is the lone pair on a least electronegative atom? If it is, it's definitely more basic. So 3 is true. And then 4, propene, is the weakest acid in the equilibrium. So that's this here.
Yes, because of the
Is that
pKa
true?
being
Right, definitely. The pK is very positive. It's 43. So that's definitely the weakest acid. So the answer choice that goes with what we said is D. 1, 3, and 4 are the only ones that are true for this equilibrium.
Okay.
Mm-hmm.
All right. Yeah, that makes sense.
Yeah,
Could you go over 23?
sure. I'll try and go over that one. So
Thank you.
23 says, arrange the following alcohols in order of decreasing pK. Oh, decreasing pKa. So that means you're going from the most positive to the most negative pKa. So first we have this molecule.
Are we going for the most positive?
No, yeah. I'm just drawing I just drew what we're going from, so I'm just drawing out the molecules and we'll rate them based on like number. So
Okay.
4 would be we could say 4 would be the most negative and 1 would be the most positive. So this last one, OH. Now, acids, when you give away the protons, you always create what?
Resonance. Why not?
What in some you
Base.
want to look for that. You create bases, right? But you always create stable bases. So the first thing we always try to look for when it comes for the stability of the bases is 4 types of trends we look for. First, we look for if the result of the proton being an electron being donated will result in resonance, right? If the base could resonate, that means that before the proton was donated, that molecule was a very strong acid. So we look for resonance. What we also look for is in some cases the inductive effect. This is when we have halogens attached near the OHs as well. So the inductive effect also plays a part in stabilizing the negative charge that's created. So that also increases the molecule's acidity as well. Another thing we look for is, so there's resonance, the inductive effect. Electronegativity is definitely one of them.
Yeah, but in this case,
Yeah, so like in some cases, if we don't have resonance and the inductive effect to play a part, the more electronegative atoms, they always handle the negative charge better. So that helps with stabilizing the base. And for the last one, we look at what was it?
hybridization.
I always forget the- Yeah, I believe hybridization. I don't know if it's hybridization. The last one always slipped my mind, and that's like the most easiest one you can look for. If I'm not mistaken, I think that has to do with atom size. Well, I forgot the fourth one, but the first three here is always what is mostly going to result in anyway. So you look for resonance, if the inductive effect plays a part in stabilization, and if the electronegativity plays a part. So then, now let's rank them. Which one of these molecules can we definitely say would be rated as 1?
Or positive. The OH.
Right, the one with just the OH and not like nothing else. This one can be rated 1. It only has the electronegativity to base itself off of. Versus the other molecules, we do see double bonds, triple bonds, and double bonds and triple bonds. So this one has the most positive pKa. So now let's look at the other ones. You have this OH with just the double bond, the OH with the double bond in between, and then the OH here with a triple bond. So which one could rank as 2?
I think the OH with a double bond.
Right.
Near to the
Alkenes. So the alkene is pulling electron energy away, but remember, alkynes have it definitely has much more of an electron energy pull than the double bonds do. So the OH with the double bond would be 2. The OH with the triple bond would be 3. And that leaves this OH here in the middle. This would be the most acidic. I think so.
red.
Why is that the most acidic? Sorry.
Mm-hmm.
No. Why is that the most acidic? The
Oh.
third one.
Oh, because of resonance. You see where the double bond is here?
Yeah.
It can resonate. So when this proton is donated, when the proton is donated here, the electrons on oxygen, one of them, they can resonate. So because of that, that means we created the most stable base in 4, which means that the molecule before the proton was donated is definitely the most acidic, which is the more decreasing pKa.
Okay.
Any questions?
No.
All right. Well, it is 4. So if you do have any other questions, you could email me. I do have office hours on Monday, so I will definitely get a chance to look at the practice exams a little more, and then we could keep studying for your exam coming up on Thursday.
Okay. What time is your office hours again? It's 2 to 4 on Monday?
Yeah. Yeah, office hours is going to be from 2. I mean, Monday is going to be from 2 to 4.
Okay. Alright. Yeah, thank you, Mr.
Yeah.
Kemi.
You're welcome.
Alright. Have a good day and a good weekend.
You too.
Alright, thank you.
Any questions, just email.
Alright. Thank you. Bye-bye.